Okay, so far that is the detailed discussion of the two-dimensional convolution, and then why this operation is also known as a two-dimensional operation. Okay, if you see that the operation is not so difficult. Okay, just again it's a sum of product, and then you need to slice the windows to the entire image by having something like this. Okay, even if you don't understand the mechanism behind what actually is all about, how does that relate with the one-dimensional convolution, okay, you can also know how to, okay, the most important thing is you know how to compute a two-dimensional convolution given the input image, and this is the given the kernel of the image or the windows of the image like this one. Okay, because the operation is like you is like what you have seen in this slide there. Okay, that's how we do. Okay, even you don't understand the fundamental behind it, this is how you compute each and every two-dimensional operation. Okay, so okay, this is the explanation about the same things there. Okay, process of multiplying, summing, and translating. Okay, the translating here is a sliding process that I always mention. Okay, multiplying, summing, and translating of mass with respect to the underlying image is also known as a two-dimensional convolution operation. Okay, we have to go deep into that discussion in the earlier slide there. And again, like I said, the size there can be 3 times 3. Of course, in this example we talk about a 3 times 3 window size, and you can also have 5 times 5, 7 times 7. Okay, you can go big there, and so as have a symmetrical center. Like I said before, the filter coefficient is always in a symmetrical structure. Okay, that's why we skip of doing the flipping process there because of the symmetrical structures. Okay, this is the expression of the two-dimensional convolution. Of course, without having understand about this operation, you also know this have been represented by these sliding operations there. Okay, the same things like the one-dimensional convolution that we have discussed before. Okay, before we start discuss about what are the several type of kernel-based processing, I will like to ask you to try this question. Okay, given this is the input image, okay, this is the input image F, and this is the window or the kernel WXY. Find the output image GXY. Okay, after applying the convolution, two-dimensional convolution between your fxy and your wxy. So what are the output image G when you applying the input image F, which is convolved with WXY. Okay, this is WXY. Okay, just ignore about this one. Okay, when you see this kind of representation, okay, then you must remember there's a factorial value over there, 1/16. Actually 1/16 must multiply with this each and every element inside here. Okay, this one should be 1/16, this one 1/16, 1/16. Okay, this one 2/16. Okay, just remember that. Okay, when this factorial is outside there. Okay, in other words, if you want to make sure this factorial inside this one, you just delete this one. Now the coefficient is in this form. Okay, because in general, in many textbook in image processing, they always bring the factorial outside, so you can see a very a beautiful round value number, a single number inside the matrix element. So they just take a factorial and bring it outside. but now I just let's ignore this point. I just bring it inside. Now everything, each and every coefficient there should be divided by 16. Now compute the output image when you do the convolution between your F and W there. Okay, and then one things you need to remember is that again, like I said, you just ignore the border. Okay, you just draw back the size of the output like this one, output matrix like this one, and then you just ignore the border. You just process from here to here. Okay, so hopefully you can try this in our live worksheet there. Okay, in our live worksheet, before you start the next video lecture. Okay, and this one will be considered as the proof of attendance.